The hardness of subset sum can be used to establish the hardness of a range of scheduling problems, including some that do not obviously involve the addition of numbers. Here is a nice example, a natural but much harder generalization of a scheduling problem resolved in section 4.2 using a greedy algorithm. Suppose we are given a set of n jobs that must be run on a single machine. Each job I has a release time Ri when it is first available for processing, a deadline Di by which it must be completed, and a processing time duration Ti. We will assume that all of these parameters, Ri, Di, and Ti, are natural numbers. In order to be completed, job I must be allocated a contiguous slot of Ti time units somewhere in the interval between the closed interval between Ri and Di. The machine can run only one job at one time. The question is, can we schedule all jobs so that each completes by its deadline? We will call this an instance of scheduling with the release times and deadlines. So here's the lemma. 8.24 Scheduling with the release times and deadlines is NP-complete. Proof: given an instance of the problem, a certificate that it is solvable would be a specification of the starting time for each job. We could then check that each job runs for a distinct interval of time between its release time and deadline. Thus, the problem is in NP. We now show that subset sum is reducible to this scheduling problem. Thus, we consider an instance of subset sum with the numbers W1, W2, W3 until Wn and a target capital W. In constructing an equivalent scheduling instance, one is struck initially by the fact that we have so many parameters to manage: release times, deadlines, and durations. The key is to sacrifice most of the flexibility, producing a skeletal instance of the problem that still includes the subset sum problem. Let S equals to the summations of Wi, summing with index I starting from 1 to n. We define jobs 1, 2, 3 onto n. Job I has a release time of 0, a deadline of S plus 1, and a duration of Wi. For this set of jobs, we have the freedom to arrange them in any order, and they will all finish on time. We now further constrain the instance so that the only way to solve it will be to group together a subset of the jobs whose durations add up precisely to W, capital W. To do this, we define an n plus first job. It has a release time of W, a deadline of W plus 1, the capital W plus 1, and a duration of 1. Now consider any feasible solution to this instance of the scheduling problem. The n plus first job must be run in the interval between the closed interval of capital W and capital W plus 1. This leaves capital S available time units between the common release time and the common deadline, and there are S time units worth of jobs to run. Thus, the machine must not have any idle time when no jobs are running. In particular, if jobs I1, I2, I3 until Ik are the ones that run before time capital W, then the corresponding numbers Wi1, Wi2, and so on until Wik in the subset sum instance add up to exactly capital W. Conversely, if there are numbers Wi1, Wi2, Wi3, and so on until Wik that add up to exactly W, then we can schedule these before job n plus 1 and the remainder after job n plus 1. This is a feasible solution to the scheduling instance. Caveat: subset sum with polynomially bounded numbers. There is a very common source of pitfalls involving the subset sum problem, and while it is closely connected to the issues we have been discussing already, we feel it is worth discussing explicitly. The pitfall is the following. Consider the special case of subset sum with n input numbers in which capital W is bounded by a polynomial function of n. And now, assuming P is not equal to NP, this special case is not NP-complete. It is not NP-complete for the simple reason that it can be solved in time big O of n times capital W by our dynamic programming algorithm from section 6.4 when capital W is bounded by a polynomial function of n. This is a polynomial time algorithm. All this is very clear, so you may ask, why dwell on it? The reason is that there is a genre of problem that is often wrongly claimed to be NP-complete even in published paper via reduction from this special case of subset sum. Here is a basic example of such a problem, which we will call component grouping. Given a graph G that is not connected and a number k, does there exist a subset of its connected components whose union has size exactly k? Incorrect claim. Component grouping is NP-complete. Incorrect proof. Component grouping is in NP, and we will skip the proof of this. We now attempted to show that subset sum, which is polynomial time reducible to component grouping. Given an instance of subset sum with the numbers W1, W2, W3 until Wn, and target W, we construct an instance of a component grouping as follows. For each I, we construct a path Pi of length Wi. The graph G will be the union of the paths P1, P2, P3 until Pn, each of which is a separate connected component. We set k equals to capital W. It is clear that G has a set of connected components whose union has size k if and only if some subset of the numbers W1, W2, W3 until Wn adds up to W. The error here is subtle. In particular, the claim in the last sentence is correct. The problem is that the construction described above does not establish that subset sum is polynomial time reducible to component grouping because it requires more than polynomial time. In constructing the input to our black box that solves component grouping, we had to build the encoding of a graph of size W1 plus W2 plus W3 and so on plus Wn, and this takes time exponential in the size of the input to the subset sum instance. In effect, subset sum works with the numbers W1, W2, W3 until Wn in a very compact representation, but component grouping does not accept compact encodings of graphs. The problem is more fundamental than the incorrectness of this proof. In fact, component grouping is a problem that can be solved in polynomial time. If n1, n2, n3 until nc denote the sizes of the connected components of G, we simply use our dynamic programming algorithm for subset sum to decide whether some subset of these numbers, the set Ni, adds up to k. The running time required for this is big O of c times k. Since c and k are both bounded by n, this is a big O of n squared time. Thus, we have discovered a new polynomial time algorithm by reducing in the other direction to a polynomial time solvable special case of subset sum.